So we're in section 12.5 and I'm going to do a problem that will help with a suite of problems number 51 through 59. Are the planes 3x minus 2y plus z equals 1 and 2x plus y minus 3z equals 3 parallel, perpendicular, or neither? If neither, find the angle between them and write the parametric equations for the line of intersection of the planes. So this problem here is review actually of a lot of stuff in the guided notes, but I wanted to do a bit of review just to kind of try to solidify things a little bit. So as you go along here, if you can out loud, I guess if you want to, sort of contribute to the conversation here on what some of these things should be, that would be awesome. So first of all, we got our planes. A lot of times planes are written in this fancy script so that plane names so that you distinguish it from a point. So anyway, to determine if two planes are parallel, perpendicular, or neither, it turns out we're going to use our normal vectors to those planes. And we use that to write the equation of the plane, and we use it for a lot of things. So we'll start there and then we'll talk about the particulars. First of all, the normal vectors are very easy to get from the equation of the plane. It's just the coefficients here in the simplified form. So we'll let n sub 1 be the vector that's the normal vector to plane 1. And that's going to just be 3, negative 2, 1. And that's it. So that's really nice. If you don't know that, you're going to be lost. Really important detail. The normal vector to the second plane will denote as n sub 2. So that's just going to be 2, 1, negative 3. All right. So in order for the two planes to be parallel, what we need to check is if their normal vectors are parallel. And so to do that, one thing you can check is if one of the normal vectors can be found by taking a scalar constant times the other one. So we'll do that here. When I say do, I don't really mean actually doing. Just look at the two normal vectors and notice with the two components we can already determine they're not parallel, because the way I would get from 2 to 3, I could find that constant to multiply 2 to get to 3. And that would be a positive number, but to get from y to that's equal to 1 to negative 2, I'd have to multiply by negative. And so that just can't, it's not going to jive. So you could go through some process like that. You don't necessarily have to show work. It's good to write down, your thinking here in writing this relationship, but no such C exists. Okay, they're not parallel. What about perpendicular? So to determine if the two planes are perpendicular, again, continuing with this theme, are the normal vectors to those two planes perpendicular? And I'm not going to go in the rationale here. That was something that was kind of explored with a figure that I had on the handout and whatnot. So anyway, how do we tell if two vectors are perpendicular or orthogonal? What we do is we take their dot product and we see if it's equal to what? We see if it's equal to 0. That's a pretty easy thing to do. So let's just do it. What you do is you match up the components, multiply them, add them up. So I'll just write that out quick. 3 times 2 plus negative 2 times 1 plus 1 times negative 3. So we'll get 6 minus 2 minus 3, which is 1. And that's not 0, so they're not perpendicular, which means they're neither. And that's the answer to our first question. Now, because it's neither, we have to do parts 2 and 3 here. Find the angle between them. So that's the next part. Finding the angle between them. We're going to use another thing from the past, so this is a really good review problem for things that we did earlier in this chapter. So to find theta, remember these are normal vectors. So to find, first of all, the angle theta between the planes, it's going to be the same theta as between the normal vectors. So we're going to find theta, the acute angle between the planes, by finding, same as theta between, or the normal vectors of those planes. So these are vectors. They mean something special, but remember they are vectors. And so to find the acute angle between two vectors, that's where something from the past comes in. We're going to use this cosine of theta equation, and then it was specifically written in terms of vectors, like a generic vector, but now we're going to write it in terms of our normal vectors to the plane. So here it is, dot product between the normal vectors over the magnitude of the normal vectors multiplied. We have the dot product, that's from above, it's just 1. But the magnitude is something I'm going to do a bit of side work to do because it's kind of a lot to write in that fraction. So what is the, again, another review thing, the way I can find that magnitude is just take each component squared, add them, take the root. So what that's going to be is 3 squared plus negative 2 squared plus 1 squared. You do that and you get root 14. We need to do this for the second normal vector as well. So doing that, we're going to have 2 squared plus 1 squared plus negative 3 squared. Turns out that's also square root of 14. So now let's put this all together. Cosine of theta is equal to 1 over root 14 times root 14, which simplifies to 1/14. So this isn't going to be a exact radian business, so let's just go ahead and find this in degrees approximately. But first I'll just kind of write this out a little bit better. Arc cosine of 1/14, or inverse cosine, and this is approximately equal to, in degrees, 85.9 degrees. So we can box that off.